going to talk about concavity. Now, really, the only time we've talked about concavity so far is with parabolas, concave up, concave down. But concavity, if you like, is a measure of curvature, or a better way of saying it is change in slope with respect to x. So how quickly does the slope change? And so that creates the curvature. If we have a look at our standard parabola there, y equals x squared, it starts off on the left-hand side with a reasonably steep negative slope. But then it's still negative, but it's getting shallower and shallower and shallower. So the actual slope, if we think of the size of it, it might be going from, oh, I don't know, we might have started at negative 10 to negative 9 to negative 8 to negative 7. And then eventually we get to the stationary point, and it's at 0. And we get past that, and now we get positive slope. So it might start off at positive a half, positive a quarter, and it gets bigger and bigger and bigger. So basically, that's telling me the rate of change is a positive amount, because the slope is increasing in value. It's going from something that was very negative, and if we keep travelling along, it goes to something that's very positive. So it's increasing in value. So the rate of change is increasing. And similarly, if we've got a concave down one, we'd start with something which is very positive, and we get smaller and smaller and smaller, and eventually become negative. So it has a negative change in the first derivative, or change in slope. So change in slope with respect to x, second derivative measures it because it is a rate of change, but it's a rate of change of slope. Slope's measured by the first derivative. So what we're really saying is, how does the first derivative change? So we're differentiating again, that's our second derivative. So second derivative measures the concavity. So second derivative is greater than 0. We know that that slope is increasing. If we're talking about a parabola, there it is, concave up, we basically call it. It's concave up. It is a happy curve. So second derivative is positive. Yeah, it's happy. If you think back to quadratics, okay, general quadratic, ax squared plus bx plus c. Differentiate it once, we get 2ax plus b. Differentiate it twice, 2a. And so there again we say, well, hang on, if the second derivative is positive, if 2a is positive, oh, hang on, well, if 2a is positive, a is positive, and that was our definition for concave up parabola, that a was greater than 0. And so that's where it comes from. Similarly, if the second derivative is negative, then the curve is concave down. And of course we have this situation where what happens if there's no concavity there? What if the second derivative is equal to 0? It's more than likely going to be a point of inflection, but it might not be. And so that's why we say it's a possible point of inflection. We have to investigate further to see whether it actually is or not. We're only going to use the second derivative to draw a very rough sketch of x cubed plus 5x squared plus 3x plus 2. So basically we're just going to find where is it concave up, where is it concave down. It's going to be a very rough sketch. So, well, we've got to find our first derivative before we can find our second derivative. Second derivative is 6x plus 10. So I know it's going to be concave up when that's greater than 0. So x is greater than minus 5 on 3. Logically then it's going to be concave down when it's less than. So, as I say, it's a very rough sketch. There's x equals minus 5 on 3. Voila. There's a very, very rough sketch. I haven't even bothered finding the y-intercept, although that would have been easy, or the x-intercept, or for that matter, even the y value, although I know it's positive. I think I did make sure it was positive. So, okay. Let's have a look at this in a bit more, detail. Because what we can now do is combine the idea of the first derivative and the second derivative to save ourselves some time. Because if we have a turning point, now we know every turning point on a curve is a stationary point. Okay? So the first thing we can do is say this, well, if I know it's a stationary point, but I also know that it's concave up, here I am down the bottom, it must be a minimum turning point. So I don't actually need to draw the table of values. I could just sub straight into the second derivative. And if I know it's got a positive concavity, got to be a minimum turning point. Now, the table of values is still useful. I mean, if you've got a difficult function to differentiate, then don't waste time differentiating it. Still stick with the table of values. But if it's fairly easy, do it this way. And of course, if it's less than 0, concave down, here I am at the top, must be a maximum turning point. So again, we combine the ideas, we can get a better one. So let's find our turning points of this particular cubic. X cubed plus x squared minus x plus 1. We need our first derivative, we need our second derivative. Locate the stationary points. The stationary points occur when the derivative is equal to 0. So we just got to solve our little quadratic here, and we end up with minus 1 1/3. Now let's just test them. Well, when x is -1, second derivative turns out to be -4, which is less than 0. So I know it's concave down and stationary. So we've got a maximum turning point at -1, 2. Check a third. When we sub a third in, it actually turns out to be +4. And that one's greater than 0. So now I've got a minimum turning point. So it saves us a little bit of time of drawing up the table of values. Let's go back to the controversial inflection points. So what is actually a point of inflection? It's where concavity changes. Okay? So that's why it must be equal to 0. Because before you can change from positive to negative, you can't just jump, it must pass through 0. So that's the point of inflection, that point where it changes the concavity. So we could, just like we did with the first derivative, we could test either side and investigate what's happening with the concavity. So let's find the inflection point. I know it's got one because it's a cubic. All cubics have an inflection point. All cubics have an inflection point. So first derivative, second derivative, possible points of inflection. So it's a bit like classifying the maximum minimum points. First of all, you've got to locate the possibilities, which was the stationary points, then classify them. So it's the same process. Locate the possibilities. This time it's when the second derivative is equal to 0. And we just have one possibility of -1/2. Then classify it. So I'll draw up a table of values. -1/2. Same deal. I've got to pick a point on the negative side, pick a point on the positive side. I can pick any point I like as long as I don't go past any point of discontinuity or any other possible inflection point. So I know at -1/2 it's 0, it has no concavity. Left-hand side I'll use -1. Sub that into the second derivative, I get -12, so it's concave down. Testing 0, I get +12, concave up. So yes, there is a change in concavity. Okay. So you're concluding what you just did. So you've told them, right, I'm looking for possible inflection points. I've found the possibilities. I've tested them and discovered, yes, there is a change in concavity. So therefore, -1/2, 3 is a point of inflection. Okay. Horizontal point of inflection is a very special type of inflection point. It's one which is also stationary. So it's a stationary point and it is an inflection point, and I guess the classic is y = x cubed. Some people make the mistake when they're drawing their sketches to make all inflections, they try to make all of them horizontal point of inflections, but they're not. They're only ones where the stationary ones. The classic mistake, I guess, is when people draw y = tan x and they draw it through 0 and try to make it look like a cubic. But actually that inflection point has a slope of 1. It goes through at 45 degrees when you draw a tan curve. Still an inflection point, just not a stationary point. So ones that are, we call horizontal points of inflection. First derivative equals 0, second derivative equals 0, third derivative does not equal 0. Third derivative? Where did this come in? Now I'm going to let you in on a little secret. But think about it logically. Derivatives, if you like, measure rates of change. We're trying to measure whether there is a change in concavity. Well, the second derivative measures concavity. So if I want to find the change in the second derivative, I would use the third derivative. Okay. So we know possible points of inflection possible point of inflection occur when the second derivative equals 0. Now, this is the actual rule. Okay. if the first time you sub into a derivative and you get an answer that is not 0, if it's an odd derivative, so the third derivative, the fifth derivative, the seventh derivative, etc., then it is a point of inflection. Now, the vast majority of the ones that we're going to look at, we won't have to go past the third derivative. Third derivative will work. And in fact, if you have to go past the third derivative, then I'd simply just go back and test either side of the point and look at concavity rather than doing all that work. Here's the interesting one, which people don't realise. If the first non-zero derivative is of even order, it's not a point of inflection, it's a turning point. Now, I'll give you the example of y equals x to the power of 4. Now, think of y equals x to the power of 4. We know what it looks like. It's basically got that U shape, a bit flatter at the bottom, steeper at the sides. But we know there is, in fact, a turning point at 0, 0. Okay? Let's have a look at calculus. So y is x to the power of 4. Y dash would be 4x cubed. Okay. So, all right, stationary points occur, and we've located, oh, well, x equals 0 is a stationary point. We sub it into our second derivative. Oh, hang on, it's equal to 0. That's telling me there's no concavity. That doesn't make sense. Keep going. Third derivative, 24x, sub it in. Still 0. Oh, okay. It's equal to 24. It's not equal to 0. So the first time when I substituted in x equals 0, I did not get an answer of 0, was an even one. So it's a turning point. So it's a turning point. If the first time I did it, it was was the third one or an odd one, then I know it's a point of inflection. Okay? So if I go back to, did I do our example again? Okay, so in the example that we just looked at, we identified a possible inflection point. If I had kept going, the third derivative would have been 24. Well, actually, it doesn't matter what x is. If I sub that in, it's not going to be 0. Now, if you're going to use this method, so you want to make sure you explain yourself very carefully. The way I would write it down is I'd say, okay, I found my third derivative. Well, when x equals minus half, it's 24. It's always 24. That does not equal 0. Think about what that is saying. If it is not equals to 0, then it must have some value. If it has some value, that means there is a change in the second derivative of some rate. Just don't know what the rate is. I mean, yeah. So if there is a rate of change of the second derivative, there's a change in concavity. It's an inflection point. Okay. So that's the key bit. It's not equal to 0. Make sure, again, you write that, therefore there is a change in concavity. And so that people know what you're doing. You're not just writing rubbish down, you're explaining what you're doing. Okay, there is a change in concavity, so minus a half 3 was our point that we saw before. It is a point of inflection. But just like with the testing either side for stationary points, if it's difficult to differentiate, well then test either side with the second derivative. Don't give yourself more work. Only use this idea if it's going to save you time. If you've got something difficult to differentiate it, don't use it. In fact, you don't even need to test the second derivative either side to prove inflection points. You can test the first derivative either side to prove inflection points. Because if you've got a curve that's increasing, and then your possible inflection point, it's got some value, it doesn't really matter, but then it's increasing. Well, if it's increasing, then increasing, we must have just gone through an inflection point. So you can actually test the first derivative either side to prove it's an inflection point. There's also logic, but if you've got a continuous curve and you've got a maximum point and a minimum point, there has to be a change in concavity in between there somewhere. And if there's only one possible point of inflection in between them, well, that's got to be it. Because there's no other possibility, and we know one exists. So that's another way you can say, well, therefore that's got to be an inflection point.
That is